Okay, but part A wants to know the max value of this function between 0 and pi, and we have to justify why we think that. Okay, so it doesn't come out and say it, but to me this is one of those theorems. This isn't mean value theorem. What's the other one we did? That's intermediate value theorem. We did that at the beginning of the year. I'm thinking more recently. Extreme value theorem. You want the absolute biggest value or absolute smallest value? That's extreme value theorem. Now, you don't have to say anything about extreme value theorem, but it helps because extreme value theorem tells us that the max and min value will either occur at an endpoint, like 0 and pi, which you probably didn't think to check, would be my guess, or at a critical number, because that could be a relative max, and sometimes relative max are extreme max. Okay, so critical numbers, this term that's coming up all the time now, are when the first derivative is 0 or undefined. So you should have taken the derivative. This would be like so. So probably a point for the derivative. Now I know this is hard for you guys to like grade, but again, this is just practice. But technically, if you mess up the derivative, yes, you would lose that point if there was a point assigned to it. But if you use that correctly throughout the rest of part A, you can get the other parts. So, okay, and then critical numbers are where this is undefined or 0. Sign is never undefined. You think about going around the unit circle, sign always has a value. So setting this equal to 0 is sometimes worth a point. You get down to here, sine of 2x is 1. So we have to think of numbers that or angles that we can multiply by 2, so that if we took the sine of them, we get 1. So kind of the algebra approach to that would be just temporarily ask yourself, when is sine 1? So sine is only 1 at pi over 2. But then you have to go back and say, well, wait a second. This wasn't sine x. This was sine 2x. So I didn't solve for x. I solved for 2x. Divide both sides by 2, and it looks like that would be pi over 4. And then you can always plug it in to check. If I plugged in pi over 4 here, times that by 2, that would be pi over 2, and the sine of pi over 2 is 1. Need the unit circle here. But since I've recognized this as extreme value theorem, I know which 3 points to test pretty quickly. So if I was to plug in 0 into the function and find its y value, this would be 0 plus the cosine of 0, which is 1. Yeah.
Back at sine 2 equals negative 2. Whenever you divide, or why'd you divide negative 2 by 2? Or why'd you divide negative 2 by negative 2?
Well, I subtracted this over. So when I subtracted this over, it became a negative 2.
Yeah, okay.
And then I divided that.
Yeah, okay.
No, that's fine. Sometimes I try to do the arithmetic part quicker so we can focus on what's new. That's all. If we try to plug in pi, we get 2 times pi plus the cosine of 2 pi. And what is the cosine at 2 pi? Where's 2 pi on the unit circle? This is 1 pi. 2 pi is all the way around. So cosine is 1. And then pi over 4. So 2 times pi over 4 would be pi over 2. plus the cosine of 2 times pi over 4, which would be the cosine of pi over 2, which is 0. So I guess these are a little harder to decipher, but what looks like it would be the biggest y value? One more time? 2 pi plus 1?
Yeah.
Did you say plus 1?
Yeah.
Okay.
Sorry, I said really fine.
No, it's fine. I heard plus 4, but so that is the max value. They didn't say when did it happen. They wanted to know what it was. So now this is a non-calculator question, but if you graph it, you can see that the biggest y value certainly happens at the far end. So most of the time critical numbers are going to be your max value, but if they're testing extreme value theorem, they're really going to want to see if you tested the endpoints as well. Okay, so if 9 points are set aside to this FRQ, again, you probably get 1 point if you got the derivative right, maybe 1 point if you set it equal to 0, probably 1 point if you did this candidates test. This is the easiest way to show your work on this type of question. If you're trying to explain that in a sentence, you have to say, well, why didn't you try pi over 2? Why didn't you try 3 pi over 2? You have to, your explanation has to be comprehensive enough. But the candidates test, you can just test the endpoints and the critical numbers. Look for the biggest y value if you want max value. Look for the smallest y if you want the smallest. Okay, part B. Explain how the conditions of mean value theorem are satisfied for f from 0 to pi. So mean value theorem only works if the question is not jumping around everywhere. So it is continuous from 0 to pi. And differentiable, because if you have any sharp turns, that also messes up the average. 0 to pi. Technically, the differentiability doesn't have to include the endpoints. I know we haven't talked about that much, but I had that in your notes there. So because of that, that's why mean value theorem guarantees there's a value of x where this happens. So hopefully you guys are pretty quick at setting it up at least. Mean value theorem says the instantaneous rate of change is equal to the average rate of change. I feel like that step should be a little easier because you guys had so much practice from that circuit. Okay, if I plugged in pi into the function, I get 2 pi plus 1. If I plug in 0, I get 0 plus 1. All of this is over pi. So the instantaneous rate of change, which is derivative, is equal to the average rate of change which looks like that. If I plug in 0 to the function, where is the function? That would be 0 plus 1, which is 1. Yeah, it should be minus 1. So these cancel out. Subtract 2 from both sides. Divide both sides by -2. And it looks like our answer should come from when sine 2x equals zero. That's what y'all have? Okay, and sine is 0 here and here. 0 and pi. But this wasn't x, it was 2x. So you need to divide both sides by 2 to make that a 1. So I would probably say 0 and pi over 2. So I don't know what this looks like, but the average rate of change, which is what we did on the right side, the slope, apparently we had the same slope at 0 and the same slope at pi over 2. They have the same slopes at those instances. Okay, any follow-up to any part of that FRQ? Anything you need cleared up? Okay.
When it says explain how the conditions of the mean value theorem are satisfied by f for that interval, is that basically just like what we did, like
This.
saying that? Okay.
Because if your function's not continuous, like, I don't know, let's say there's a hole here. Well, so this average rate of change, mean value theorem says it occurs at least once. But if this is not continuous, so maybe the graph does like this, it does like an asymptote or something. Like now there's not a spot that's guaranteed to have that same slope because it's jumping around. Likewise, if it's not differentiable, like it's got a cusp, the average rate of change might be this, and there's no x value that has that slope. We either have this slope or we have that slope, but never does it equal this slope. Never are those equal. So you can't have a cusp.
So you're saying like, it's the conditions are satisfied because you can take the first derivative of it?
Because it's continuous over the whole interval and it's differentiable on the open interval. Like it doesn't, you don't have to be able to take the derivative of the endpoints, but it needs to be continuous on the endpoints. If it's not continuous on the endpoints, then 0 couldn't be a solution because that's the endpoint.